Hello and welcome to the next section of your L1 training course. In the first part of this section, we will introduce the fundamentals of Lidar technology with specific emphasis on the technical parameters of the Zenmuse L1. This will include details about the return mode, sampling rate, scanning mode, alongside an introduction to all of the parameters. We will then apply our knowledge of L1 parameters to specific mission types, providing recommendations for each. In the final part of this section, we will provide detail on the calibration procedure of the L1's IMU. Firstly, we will begin with a short introduction into Lidar technology. Lidar stands for light detection and ranging, first hitting the market in the early 1970s, focusing on single beam profiling with the applications of bathymetry. With the development of GNSS technology and highly accurate inertial measurement systems, Lidar soon became an attractive option to engineers and surveyors alike, with sensors making it possible to collect highly accurate survey-grade data in areas that terrestrial surveying methods were not easily employed. Fast forward, an aerial-mounted Lidar now has applications across a range of surveying and mapping verticals, including flood monitoring, terrain modelling, coastal mapping, and 3D modelling. A Lidar scanner uses light in the form of a pulsed laser to measure the time difference between an emitted pulse and a return pulse. Knowing the position and orientation of the sensor, this can then be used to determine the XYZ coordinates of the reflective surface. On a large scale and with high point sampling rates, Lidar can be used to generate three-dimensional point clouds with millions of individual data points. Depending on the specification of the sensor and its ability to capture multiple returns and RGB data, the resultant point cloud can be visualized by these characteristics. Additionally, the point cloud can also be viewed based on intensity and height as a graduated colour scale. These systems have traditionally been very large and heavy, therefore requiring manned aviation, satellite or larger UAVs in order to become airborne. However, over recent years and with the advancements of small unmanned aerial systems, the deployability of Lidar is significantly easier. With the DJI L1 now at the forefront of the industry, Lidar has never been more affordable. And combined with the DJI Matrice 300, you can achieve highly accurate and efficient data sets at a relatively low cost. Taking a closer look at the Zenmuse L1 and the parameters used when setting up a mission, we will now head over to the Enterprise Smart Controller and into the application DJI Pilot. Later in this section, we will relate all of the following parameters to our specific mission recommendations. However, first we will provide an overview of their purpose. In order to load all necessary L1 parameters, we will first select an area of interest. The area we will be looking at is a local farm located in Northumberland and will be used later in the course, particularly when post-processing the data. We will also take a detailed look at specific mission types later in this module. Firstly, select L1 as the camera and Lidar as the mapping task. At this point, it is worth noting that the L1 can be used as a photogrammetry tool without the necessity to capture Lidar data. Therefore, if this is all that is required, then you need to select photogrammetry mission only. With the L1's Lidar sensor now selected for data collection, you will notice flight lines have now been generated, with the green line shown where data capture will take place and the yellow line shown where the calibration will take place. These lines will adjust as we change each setting throughout this module. Likewise, the mission global parameters located at the bottom of your screen will also be affected by the flight mission setup. Working down from the top, we first come to our point cloud density, which effectively details the number of points per square metre. This is not a configurable parameter, but is something you can manipulate, as it is calculated based on a combination of flight altitude, flight speed, overlap, return mode and scanning mode, all of which we will cover in greater detail in a few moments. Next up, we have the ortho GSD, displaying the ground sampling distance for the photogrammetry data we will collect in tandem with the Lidar data collection. Although the GSD parameter will always be present, it is important to note that RGB colouring needs to be switched on in order to capture RGB images. Again, we will show you where to find this soon. Photogrammetric ortho GSD is directly affected by one main parameter in your flight settings, and that will be flight height. If the lens was interchangeable or the camera held a zoom lens, then this would also affect the GSD. But in the case of the L1 sensor, the lens is fixed. Skipping past IMU calibration, we next have terrain follow, a feature used to fly with a consistent distance away from the ground surface. We will provide a tutorial for this later in this module. Altitude can be detailed in two ways. A standard DJI Pilot will display this altitude as above takeoff point, also known as ATL, but you can also display altitude above sea level, measured by the world's Earth GeoModel, EGM96. This is then followed by some of the standard automated mission planning settings, including flight route height and target surface to take off, both measured in meters, as well as the takeoff speed and speed, both measured in meters per second. Below that we have a setting called elevation optimization, a setting that when enabled, the aircraft will fly to the centre of the mapping area on completion of the flight. From there it will capture a series of oblique images to increase the elevation accuracy. Given the nature of an automated mission, there are several commands that you can set up upon completion of your data collection, including hover, return to home, land, and go straight to route start point. Whilst return to home is likely to be your most commonly used, if you have some standard stills to collect or other requirements to fulfill, then you can keep the drone in the air instead of bringing it back to your base. Before we move into advanced settings, you'll find the longitude and latitude located at the bottom of your flight settings. Your mission's location can be manually adjusted using the controls in the bottom right hand corner. Inside of advanced settings you will first find the side overlap, which as standard will be set at 20%. With LiDAR, a process of direct measurement, as opposed to a reconstruction process like photogrammetry, overlap is significantly less important, therefore a lowest percentage can be selected. Later on we will discuss occasions where higher overlap is required. When operating within a deer sensor angle, course angle is almost irrelevant, as it will only determine your flight route. Therefore, selecting an angle that captures the data in the most efficient manner is the main goal. This would usually be parallel to the largest side of the survey. During L1 data capture, the sensor will not collect data when the IMU is calibrating, depicted by the yellow flight lines. The margin can be used to increase and decrease how far your flight lines overlap your area of interest. This unit is measured in meters. The final parameter located in your advanced settings is the photo mode, which allows for control over how RGB stills are captured in a photogrammetry process. You can set this by timed interval or distance interval. Whilst this does not apply directly to LiDAR data capture, both photogrammetry and LiDAR can be captured at the same time through a setting we can display in just a moment. Finally, we can head over to the payload settings, where we will find the parameters that specifically relate to the way the L1 sensor will record and store your data. First we have the return mode, also known as the echo mode. The three return modes available on the L1 are single, dual and triple echoes. Depending on the echo mode selected, this can also alter the point cloud sampling rate. In single and dual echo modes, the maximum sampling frequency is 240,000 kHz, meaning that 240,000 laser beams are emitted per second. In triple echo mode, the maximum sampling frequency is 160 kHz. In theory, this should measure as 480 points per second, but in practice it records a much smaller number of measured points. A combination of dual echo mode and a sampling frequency of 240 kHz would derive the highest number of measured points for a dataset. Therefore, in practice, we wish to recommend dual or single echo mode if you wish to derive a greater point cloud density, whereas triple echo mode is best suited to measure in areas in dense vegetation. Selecting the triple echo mode ensures that the sensor is measuring multiple returns from the surface, which is useful when penetrating dense forest canopies. The LiVox LiDAR on board the L1 supports a non-repetitive scan mode and a repetitive scan mode. Each scanning mode has very unique and different patterns that are tailored to different applications. As previously seen in section 1 and in your course handbook, the non-repetitive scanning method follows a spherical motion, whereas the repetitive has a more linear effect. The field of view, also referred to as the scanning angle, represents the angle covered by the LiDAR sensor, or the angle at which lasers are emitted. The field of view varies depending on the scan mode detected. For a repetitive scan, the vertical field is narrower, but the accuracy is higher. This will involve the L1 scanning repetitively in a rectangular line. Alternatively, a non-repetitive scan type could be selected, meaning that the vertical field is narrower, but the accuracy is higher. This mode is recommended for capturing data of complex structures or building facades, and works well with oblique mapping missions. Last but not least, we have the RGB colouring setting, which when selected colourises non-RGB L1 point clouds using image data collected by the L1's RGB sensor. In turn, this also captures images in a photogrammetric process, as referred to throughout this section so far. This data can not only be used to colorise the LiDAR point cloud, but also to generate the photogrammetric orthomosaic point cloud and 3D mesh. In the next few sections, we will be taking a look at what settings are recommended for specific mapping applications. The first and most common application that we'll go through is for the purposes of topographical mapping and/or vegetation penetration. Whilst they are two different applications, their flight planning parameters are very similar. Typically a polygon-shaped area, we will select mapping as our choice of mission. Using the touchscreen, navigate to your proximate area of interest and tap the screen once. This will bring up a blue data capture box. Using the vertices, reshape the box to cover your area of interest. Once the L1 LiDAR sensor has been selected, you'll need to ensure your IMU calibration is selected too. You'll notice that the yellow calibration lines appear at the edge of your survey area. With topographical surveying, accuracy is of the highest importance, whereas with forestry mapping, sub-canopy point density takes its place. However, both of which are improved with lower flying heights. Therefore, it is recommended that you aim for a 50-meter flying height. Although theoretically increasing the flying height decreases the accuracy of the dataset, Heliguy have validated the L1 at 100 meters inside of the specification of the system. On that basis, if efficiency does need to be considered, flying height can be extended up to 100 meters. In areas of heavy vegetation, you may also want to fly lower than 50 meters to increase the density of the point cloud beneath the tree canopy. For this generic example, you will maintain a 50-meter flying height. Our flight speed should be set at 10 meters per second or less for optimal results. If efficiency is no barrier, then you will obtain a greater point cloud density with a lower flight speed. Jumping down to our payload settings, we next need to select the return mode. For highly vegetated areas, including forested areas, it is best to select triple returns to achieve the best terrain coverage. However, if completing a topographical survey in an area without significant vegetation coverage, then it is best to select either single or dual. This should then automatically change your sampling rate to the highest possible for that echo. If you would like a smaller point cloud density, then you can select a lower sampling rate. However, for most cases this should be kept the same. For both applications, the best scanning mode should be repetitive, as this achieves a better point cloud density and improved accuracy, lending itself to topographical surveying. Although preference, we would also recommend RGB colouring is enabled to provide a form of colour realistic output. This would also mean that RGB stills are collected which can be used to generate an orthomosaic. In the advanced settings, we should then select a higher degree of overlap. 50% is recommended. The reason for this is because photogrammetry requires a larger amount of overlap, and for the successful data capture of both LiDAR and photogrammetry, 50% is the DJI recommended figure. If RGB colouring is not required, then a minimum of 20% is required to maintain the specified point cloud density. The increased overlap also increases the point cloud density, especially good for forestry mapping. As we are working within a deer camera angle, the coarse angle only affects efficiency. Finally, we also recommend that elevation optimization is selected to allow for the collection of a small sample of oblique images at the end of the mission. If processing via DJI Terra, this will improve the elevation accuracy of your photogrammetry data. Now that all settings have been selected, you will find your mission distance, estimated time of completion, waypoints, photos and mapping area located at the bottom of your screen. Please bear in mind that this does not account for battery changes or pauses in the mission. For environments with significant terrain undulations or 3D structures, standard Nadir data will not provide comprehensive point cloud densities on the sides of facades. Therefore, the L1 sensor angle must be set at an oblique angle. In DJI Pilot, oblique missions are split into 5 sub-missions. The first of those will provide Nadir data capture directly over the area of interest, whereas the subsequent 4 missions displace the flight path in each of the 4 directions: east, west, south and north. This is necessary because an oblique sensor angle would essentially eclipse the area at the closest edge of the survey, and with more severe angles, less and less of the area of interest will remain inside the mission's data collection. DJI Pilot essentially considers both the flight height and sensor angle to determine how much of an offset to apply. Taking a closer look at the settings, we first come to the gimbal pitch angle. This parameter varies depending on the features present on site. If there aren't any steep or large variations in height, then selecting an angle closer to -90 degrees would satisfy. We would recommend -75 degrees for generic examples. However, if working in an environment with significant elevation changes and/or 3D structures, such as buildings, then a more severe oblique angle would be recommended. For this example, we would recommend -60 degrees for generic cases, but in certain scenarios this can go as low as -45 degrees. Increasing the severity of the sensor angle essentially generates a better perspective for the sensor to capture data on the sides of facades. Although the point cloud density for your LiDAR data won't be affected by the gimbal angle, the photogrammetry will be less detailed, meaning the GSD will be far higher for the oblique data capture. At this point, it is worth noting that you can select or deselect any of the 5 submissions. Therefore, if you only need oblique data for angles north and south of your dataset, then you do not need to collect the east and west images. This is especially useful in examples such as quarries that may have one severe or linear cliff face. With oblique LiDAR and indeed photogrammetry datasets, flight height is best kept as close to the tallest structures as possible. For example, if working in an urban environment, fly 10 meters higher than the tallest structure to achieve the highest point cloud density on structure facades. Similar to topographical surveying, a lower flight height will provide you with a more detailed point cloud. Therefore, for 3D modelling applications, it is recommended to fly as slow as possible. 5 meters per second is recommended. If RGB colouring or independent photogrammetric data is also required, then it is important to remember that a 50% overlap is essential. However, if neither is required, then this can be reduced to 20% with the loss of point cloud density. Assuming that there is very little vegetation, it is recommended that either single or dual returns to be used. As a dual echo does not diminish the point cloud density, we recommend that this is used for most scenarios, as there is likely to be some vegetation coverage even in the most urban environments. Triple echo mode will reduce the sampling rate, therefore this is not recommended. It is also recommended that a repetitive scanning pattern is used to ensure maximum coverage of facades. Terrain follow is particularly useful for areas with sloped or uneven terrain. As standard, the Matrice 300 will fly with a consistent height above the takeoff point. Therefore, if you take off on the top of a hill, your point cloud density will be far less than what DJI Pilot specifies. Likewise, your GSDs will be a lot larger. Therefore, for the example of a hill, it is best practice to maintain a consistent height to the surface of the Earth to obtain the desired point cloud density. To do this, terrain follow can be used. It is important to note that terrain follow fundamentally relies upon RTK connectivity, therefore it is not possible in a post-processing workflow. Connection to network RTK or to the DRTK2 is required. You'll next need to select a DSM file, also known as a digital surface model. This data may have been collected from a previous survey or from an online national LiDAR resource. Whilst an automosaic collected using photogrammetric methods is the most common approach, you will find the UK's online database in the case note below. DJI Terra can be used to generate a DSM file by collecting 2D data of the target area and performing a 2D reconstruction in DJI Terra with fruit tree mode enabled. A GSD DSM.tiff file will be generated in the map folder of the missions, which can be imported into DJI Pilot app for terrain following. A DSM file can be imported using the SD card slot on the top of the Enterprise Smart Controller. Once selected, your height can then be denoted as terrain follow height, as opposed to flight route height. The Matrice 300 and L1 can then fly with a consistent height above the terrain instead of the takeoff point, thus improving data consistency. Finally, please note that the DSM file used for the terrain follow mission must use the WGS84 coordinate reference system rather than projected coordinates. This file should not exceed 20 megabytes in size with a preferred resolution of less than 10 meters. Although you may ordinarily think that DJI Pilot's linear flight mission mode will be best suited for powerline inspections, this is actually not the case. Waypoint missions allow for more control as well as automated calibrations, therefore data quality is much higher. When creating a route, you will be prompted by the option of setting waypoints on the Smart Controller interface or via Live Mission Record. Live Mission Record is essentially a process of manual flight prior to the automated LiDAR recording, whereby you select an accurate set of waypoints for the aircraft to follow using the C1 button on the back of the Smart Controller. This is particularly useful on sites of varied terrain to maintain a consistent height above the power lines. It also enables close proximity flight, which is very important due to the fine nature of power line structure. Although repeating the same flight you have flown manually, an autonomous flight provides a more consistent and accurate dataset. For this example, we will focus on selecting waypoints on a pre-planned flight path that involves setting waypoints before the flight, however all of the same principles apply. On the Smart Controller's flight screen, select Waypoint Mission, and then select Set Waypoints. You can rename the waypoint mission and select the M300 as our aircraft type. Under Gimbal 1, select the Zenmuse L1 sensor, followed by altitude mode as relative to takeoff point. The flight route parameters will be designed as if you were performing a routine powerline inspection. Under route settings, the speed should be set between 6 and 10 meters per second. It is best flying a little slower on this type of inspection to ensure that the complex structures of the pylon are captured by the Lidar unit. Aircraft yaw can be set along the route. Gimbal control should be manual, as you will need to manually adjust the gimbal angle at the start of the mission if looking to use oblique camera angles. Under waypoint type, we will do a straight route, aircraft stops. The information icon on the Smart Controller provides a detailed explanation of the different options available, and these can be tailored towards your survey work. Finally, IMU calibration should be on, power saving mode off, and upon completion the drone should return to home. Waypoint settings define where and when we want the L1 to collect point cloud data. At waypoint 1, under the Add Actions tool, we first want to add our gimbal pitch rotation and set the degree to be minus 90 degrees. We then need to start point cloud modelling. We also want to engage the capture of our photogrammetry data by selecting timed interval shots. Navigating to the last waypoint, we can then finish our point cloud modelling. These parameters will let the L1 collect a constant stream of data between the first and last waypoints. If there are areas that we do not wish to be included in our survey, the point cloud modelling recording can be paused and resumed. The payload settings for this type of survey will differ to topographical mapping missions. The sampling rate and return mode need to be selected 240 kHz and dual echo mode. This maximises the number of points for finer structures. RGB colouring should be enabled and the scanner mode should be set to non-repetitive, as this is best suited to capture the hard detail features. If there are any waypoints you wish to delete, you can select the waypoint of interest and then press the disposal bin icon at the top to remove this. This finalises our mission. Once we are happy with the parameters, we can save the file and begin our flight mission. For more intricate environments, whereby autonomous flight may not be possible, manual flight may be necessary in order to capture data of the area of interest. This could be areas between structures for additional detail on the sides of facades or for closer proximity flights. During a manual flight, you will need to manually initiate the calibration procedure every 100 seconds. If the sensor goes beyond 100 seconds without a calibration, then the IMU's accuracy will decrease and your data will lose accuracy. The calibration procedure involves a series of forward and backward motions at varied speeds. This should be done at the altitude of data capture. For this process, the drone will need at least 30 meters of open airspace in front of itself. It is recommended that obstacle avoidance is switched on to reduce the risk of an incident. Once the IMU calibration procedure is complete, the data capture can begin by using the record button on the right-hand side of the interface, very similar to recording a video. Once 100 seconds is up, then the recording should be stopped, the calibration process initiated, and then recording can continue. Given the nature of stopping and starting a mission, you will find that you will have multiple files containing each segment of the dataset. These files can be collapsed into one folder to allow DJI Terra to process the one complete point cloud. This section looks at importing a KML file into the DJI Pilot app. Importing a KML file is a useful feature when you're working over a large site, as well as if you want to prepare a mapping mission back in the office or on your computer. Google Earth can be used to draw a KML file. Firstly, we will need to find the survey area, so we will type our postcode into the search bracket at the top. Once we have located our area of interest, we will need to select a new project to draw up our site. We will call this project Zenmuse L1 course for now. Once we have created the project, we can draw around the bounds of our survey site using the Draw Line or Shape tool. For larger survey areas, we can break larger polygons down into smaller sections, allowing us to maintain line of sight. They can then be exported as separate KML files. However, for this example, we will just look at the one area. The placemark tool can be used to add our line in sight to the map. The measuring tool can be used to draw our survey area. The final step involves importing the KML file from Google Earth into the Smart Controller. We will need to save this file to an SD card, allowing us to load the KML into the DJI Pilot app. The SD card slot for the Smart Controller can be found in the top beneath the rubber casing. Now in DJI Pilot, we can then select the KML import instead of creating a flight route. And through access to the SD card, we can download the KML file for mission planning. The KML file will only contain the boundary data, therefore you can adjust the flight parameters depending on the application of your data collection.